Okay, Unit 4 practice exam. Here we go. Here's the solutions. Question 1. This is from Chapter 5. It's an application of systems of equations. This one happens to have two variables. We need one variable for the regular set of dumbbells and one variable for the deluxe set. So let's see. We could let x equal just the regular dumbbells. And we could let y equal a deluxe set of dumbbells. Now it says they need 24 sets. So I know one of the equations could be x plus y equals 24. And then it describes cost here. It says the regular set of dumbbells is $30, and then a deluxe set of dumbbells is $45, and it says they have a budget of $915 for dumbbells. So now all that's left is solving the system of equations. So I'm going to solve this using the elimination method. If we multiply this top equation by negative 30, for example, then that becomes negative 30x minus 30y, and then 30 times 24 is 720, so that's negative 720. Now when we add these, we get 15y. And when you take 720 from 915, you get 195. Divide by 15 on both sides now to get y equals 13. So this tells me for y we need 13 sets of deluxe dumbbells. And we're only getting 24 sets. So if you take that 13 from 24, that means that x equals 11, or we're getting 11 sets of the regular dumbbells. Okay, question 2 is from section 5.2, solving systems of equations with 3 variables. So what you need to do is add, or pick 2 of the equations and add those together to eliminate one of the variables. Now I don't have a lot of space here, so what I'm going to do is number these equations. So this top one I'm going to call equation 1, equation 2, and equation 3. Now I notice right here that equation 1 and 2, I could eliminate x. So I'm going to describe this equation 1 plus equation 2. So if I do that, what I'm doing is I'm adding these 2 equations together so that I can eliminate the x variable. So if I do that, x would cancel. Y would also cancel. Combining here, I get negative 2z and then here I would get 3 minus 1, that's 2. So combining equations 1 and 2 gives me this equation. If I divide both sides by negative 2, I get that z equals negative 1. So now I need to do a similar thing. I need to choose 2 more equations, and I need to eliminate the same variable. So I notice that equation 1 and 3 now, if I add those 2 together, I can eliminate x. So I'm going to add equation 1 to equation 3. So if I add here, x cancels. If I add here, I get 2y. If I add here, I get negative 2z. And then if I add here, I get 8. But I can put this in for z right there because I know that z equals negative 1. So this equation becomes 2y, and then negative 2 times negative 1 is positive 2. And that equals 8. So if I subtract 2, I get 2y equals 6. If I divide by 2, I get y equals 3. All that's left is to solve for x. If I take this bottom equation now, if I take this bottom equation and substitute the values for y and z, I'm going to get x, and then y was 3, so plus 3, and then minus z, which is minus negative 1, and that equals 9. So 3 minus negative 1, that's plus, so it becomes 4. If you take 4 from 9, you get 5. X equals 5. So the solution is 5, 3, negative 1. Okay, part B, I'm going to try this in a similar way. I'm going to number these equations. So equation 1, equation 2, and equation 3. So just looking at it, I noticed that I can eliminate y here from equation 1 and 3 if I add those together. So I'm going to add equation 1 to equation 3. So if I add here and here, I'm going to get 4x. If I add equation 1 and 3 there, the y's cancel. If I add here and here, I get 4z. And if I add here and here, 12 and 4, that makes 16. So now I need to eliminate the same variable from two other equations. So I'm going to choose equations 1 and 2. Problem is I don't have the same number there in front of y, so I'm going to have to multiply equation 1 and equation 2 to get opposite numbers, opposite coefficients for y. So between 2 and 3, the least common multiple is 6. So I need this to be a 6, and I need that to be a negative 6. So I'm going to have to multiply equation 1. So 3 times equation 1, I'm going to add that to 2 times equation 2. So essentially what I'm doing is I'm multiplying this one by 2. I'm multiplying that one by 3. Actually, I mixed that one up. I'm multiplying this one by 3 and this one by 2. There we go. Okay, so here we get a 9. Here we're going to get a negative 8. 9 and negative 8, that makes 1x. Here I'm going to get a 6. There I'm going to get a negative 6. So those cancel out. Here I'm going to get a 3z. There I'm going to get a negative 2z. So that equals z. And then there I'm going to get a 12. And there I'm going to get a negative 30. So 12 and negative 30. It's negative 18. So what I need to try to do now is to solve that system of equations. If I multiply the bottom equation by negative 4, let's see, 18 times 4 is going to be negative 72. So what happens here is we get the variables cancel, but the numbers on this side don't. 0 doesn't equal negative 56. So if you recall from our discussion, whenever that happens, it's an indication that there's no solution to that system of equations. Okay, part C. Equation 1, equation 2, equation 3. All right, if I want to add equation 1 and 3, that'll be helpful because x will eliminate. So I'm going to add equation 1 to equation 3. So if I do that here, x cancels. There I'm going to get 2y minus y, that's y. Here I'm going to get negative 2z and a negative z, that's negative 3z. And then here and here, I'm getting negative 4 plus 3, that's negative 1. So now we need to do the same thing. I need to try to eliminate x. So if I took these bottom two equations, for example, and multiplied here by 2, then I could eliminate x. So what I need to do is 2 times equation 2, then I'm going to add that to equation 3. So if I multiply here by 2, I'm going to get 2x here, that cancels with that, negative 2x. I'm going to get negative 2y, which is actually going to cancel with that positive 2y. Here I'm going to get 2z, which cancels with that negative 2z, and then I'm going to get a 4 here, which cancels with that negative 4. So what happens here actually is we get 0 equals 0, similar to what happened in part B, but if you remember, when you get 0 equals 0, that's an indication of infinitely many solutions. And since there's 3 variables, you're going to let z equal t. And if we take this equation here, y minus 3z equals negative 1, I can replace now the z with a t. So I get y minus 3t equals negative 1. Then if I add the 3t over, I get y equals 3t minus 1. So I know what z equals, I know what y equals, now I just need to figure out what x equals. So if I take this middle equation, for example, and write it here, I can write this as x minus, and instead of y, I can write the expression for y, which is 3t minus 1. And then here, instead of plus z, I can write that as plus t, and that equals 2. And then simplify. So combining the t's there, I get a negative 2t. So when I add it to the right side, it's going to become a positive 2t. Subtract the 1 over there to the 2, and you get plus 1. So the parameterized solution is, for x, the expression is 2t plus 1. For y, it was 3t minus 1. And then for z, it was t. All right, question 3. We have 3 types of sandwiches: Mediterranean tuna and roast beef. And using the information given, we got to figure out how many of each type of sandwich should you eat to obtain your goal of 4,840 calories and 190 grams of fat. So I'm going to let that one equal x, that one equal y, and that one there equals z. Now there's 7 days, you're going to have 2 sandwiches a day, so that's 14 total sandwiches. So if we say the number of Mediterranean plus the number of tuna plus the number of roast beef, together that's going to equal 14 sandwiches. Now for the calories, a Mediterranean chicken has 350 calories. Tuna is 430, must be the mayonnaise, and then roast beef is 290. So those are all the calories consumed in the sandwich, and the weekly goal is 4,840. Now, fat grams. The Mediterranean chicken has 18 grams of fat. Tuna, 19, and the roast beef is 5. And the weekly goal was 190. Okay, so now what we need to do is just solve this system of equations. Like we did in the last problem, the last couple problems, we need to choose two of the equations that eliminate one of the variables. So I'm just going to take equation 1 and 3 and try to eliminate, let's eliminate x. So what I'm going to need to do is multiply by negative 18 in that top equation. So the x's would cancel. And then negative 18y plus 19y, that's going to give me a y. And then negative 18z here. And then a 5z. Let's see, a 5z right there. That's going to give me negative 13z. And then when I multiply 14 by negative 18, so 14 times 18, that's negative 252. So if I take that and combine it with the 190, I'm going to get negative 62. So that's a combination of equation 1, well, negative 18 times equation 1, and then I added that to equation 3. So I need to repeat this process. I'm going to choose equations 1 and 2. And I need to eliminate the same variable. So this time I got to multiply by negative 350 so I can cancel the x. So when I multiply here, the x's cancel. When I multiply here, I get negative 350y. So if I add that to 430, I get 80y. And then here, the negative 350z is going to combine with the 290. So that's negative 60. And then there, that's 14 times 350, that's negative 4,900. So I need to combine that with the 4840. So 4840 is 4,900. That's negative 60. So now I need to take these two equations and eliminate one of the variables. I'm going to try to eliminate y. So if I multiply that by negative 80 and then add these together, y is going to cancel. 80 times 13 is 1,040. And then so that's 1,040z when I multiply here times here. So if I combine that to the negative 60, that's going to give me 980z. Now 80 multiplied by the 62, that's over here. That's 4,960. When I subtract the 60 from that, that's going to give me 4,900. So now to get z by itself, I divide by 980. So 4,900 divided by 980 is 5. So it looks like z equals 5, so that means we're going to be having 5, what was the roast beef sandwiches? So 5 roast beef sandwiches out of the 14 meals. Okay. So now if I take this middle equation here, y minus 13 times 5 now, because I know that z equals 5, that equals negative 62. So now just get y by itself. So 13 times 5 is 65. So y minus 65 equals negative 62. Add 65 to both sides, we get y equals 3. So we're having 5 roast beef, 3 tuna. That's already 8 sandwiches. There were only going to be 14 total. So that leaves 6 left over for x. So that tells me that x equals 6. So we're going to have 6 Mediterranean chicken, 3 tuna, and 5 roast beef. There it is. Okay, question 4. Remember I told you to read the directions carefully on these when it's partial fractions. This one's only asking for the form of the partial fractions. So we only have to do about half the problem. So I'm going to go ahead and factor the denominator. So here, the x squared minus 25, that factors into x minus 5 and x plus 5. Well, no, let's see, that's fully factored now. That's fully factored. So we've got 3 factors, x, x minus 5, and x plus 5. None of them are repeated, so these are all unique factors. Since there's 3 of them, I know I'm going to need 3 partial fractions. And the denominator now is just each one of these factors. So a over x, b over x minus 5, and c over x plus 5. And that's where you would stop. This is the form of that partial fraction. Okay, part B, a little different. We have x squared here, and then x squared plus 25 is not factorable. That's what's called an irreducible quadratic factor, and it's repeated. So this is case 4, where we have, case 3, we have an irreducible quadratic factor. Here we also have a repeated linear factor. So since we have 2 of these, I know I'm going to need an a and a b. That comes because I've got 2 of those x squareds. And I've got 2 of these factors, the x squared plus 25, so I know I'm going to need 2 more pieces. If you recall, this is from section 5.3, partial fractions. If you recall, when we have irreducible quadratic factors, the numerator looks a bit different. We're not going to use a's and b's and c's and d's anymore. For those irreducible quadratic factors, the numerator was actually a linear expression. So I'm going to do cx plus d, excuse me. And since it repeats, I've got to do it again. Ex plus f. So those are the 4 numerators. Now for the denominators here, these first two denominators, a and b, that comes from that factor. X squared is just a repeated factor, x times x. So the first time you write it, the factor is just the factor itself, x. And then since it repeats, you have to increase the exponent. It only repeats twice, so I'm done with that one. Now I move on to that factor, x squared plus 25. You write it once. But since it appears another time, you got to write it again, x squared plus 25 squared. All right, question 5. These are still from section 5.3, but now we're actually finding the partial fraction decomposition, the whole thing. We're not just stopping at the form. We've got to solve for those values of a, b, and c, and so on. So for part A, it's already factored for us. Since I have two factors there, I know I'm going to have two partial fractions, a over x plus b over x plus 1. Now remember, the next step is to multiply the whole equation by the lowest common denominator, which is x times x plus 1. So when that multiplies over to here, the denominator and the least common denominator there would just cancel out, so you're left with a 1. When this multiplies to that, the x's would cancel, so a would multiply x plus 1. So a times x plus 1. Now when this multiplies here, the x plus 1's would cancel, so b just multiplies with the x. So now we need to solve for a and b. Remember, at this stage, you choose what I like to call convenient values, because it doesn't matter what x equals. We're not solving for x, we're solving for a and b. So for example, if I let x equal 0, and I plug that in right there, 0 times b is 0, so the b would disappear, allowing me to solve for a. So I'm going to let x equal 0 and plug it in for all the x's. There's nothing here that changes, that just stays a 1. When I plug the 0 in right there, we get 0 plus 1, which is 1. 1 times a is a. And when I plug the 0 in for that x, 0 times b is 0, b disappears, so I know that a equals 1. If I do that process one more time, because now I need to solve for b, so I need to try to cancel the a somehow. If I let x equal -1, that'll do it. So I'm going to let x equal -1. On the left side of the equation, we just get a 1 again. That's not going to change. When I plug in the -1 there for x, -1 plus 1 is 0. 0 times a is 0, so a disappears. When I plug the -1 in there, I get -1 times b, which is -b. So this means that b equals -1. So I can take these two partial fractions, the form of them, now that I know that a equals 1, that first partial fraction is, instead of a over x, it's 1 over x. And the second one is -1 over x plus 1. Okay, for part B, these are already factored. Again, you may need to consider that the denominator might not be factored, so you're going to have to factor first in the denominator. Since there's two factors, none of them repeat, there's only going to be two partial fractions. And so we'll do a over x minus 3 and b over x plus 5 is the exact same thing pretty much as part A. I'm going to multiply now by the lowest common denominator, which is x minus 3 and x plus 5, and then multiply this LCD throughout the whole equation. So when this multiplies over to here, the whole denominator cancels with the LCD. So you're just left with 9x minus 11. Now when this multiplies there, the x minus 3's would cancel, so a multiplies x plus 5. And then when it multiplies here, the x plus 5's cancel, so b is going to multiply x minus 3. Now I want to choose some convenient values again. If I want to try to cancel a, for example, that means x would have to be -5, because -5 plus 5 would be 0. So first go around, I'm going to let x equal -5. When I plug that in here, I get -45. And then -45 minus 11 is -56. When I plug the -5 in there, I get -5 plus 5, which is 0. 0 times a is 0. So that cancels a. When I plug it in there, I get -5 minus 3, which is -8. -8 times b is -8. b, now divide both sides by -8, and I get b equals 7. Okay, so now that I know what b equals, I need to find out what a equals. So I need b to disappear. If I want b to disappear, I've got to plug in a 3 for x, because 3 minus 3 would be 0. So I'm going to now let x equal 3. If I plug a 3 in right there, I'm going to get 9 times 3 is 27. 27 minus 11 is 16. So that left side of the equation becomes 16. If I plug a 3 in for that x, 3 plus 5 is 8. 8 times a is 8a. If I plug a 3 in for that x, 3 minus 3 is 0. 0 times b is 0. Now to solve for a, I need to divide both sides by 8. So a equals 2. So my partial fractions, if I want to bring those over here now, instead of a over x minus 3, I know that a is 2. So this 2 over x minus 3. And then instead of b over x plus 5, it's 7 over x plus 5. All right, for part C, I've got 3 factors. I've got x plus 2, and then x minus 1 appears twice, so there's a total of 3 factors. So I'm going to need an a b, and a c. X plus 2 appears only once, so I just need to write it once. X minus 1 is the repeated factor. So remember what you do with repeated factors. Your first time you write it is just a factor, x minus 1. If it repeats once, then you have to write it again to the second power. And then we proceed just like in part A and part B. The next step is going to be multiply by the lowest common denominator, which is x plus 2, and then x minus 1 squared. When this multiplies over there, the LCD is going to cancel with the entire denominator. So you're just left with the numerator, 4x squared minus 7x minus 3. Now when this multiplies to the a partial fraction, the x plus 2's would cancel, so a multiplies the x minus 1 squared. Now when this multiplies the b, x minus 1 cancels with one of these x minus 1's. So the b multiplies an x plus 2 and an x minus 1. And finally c, when this multiplies over to here, the x minus 1 squared cancels with x minus 1 squared. So c multiplies x plus 2. Now we got to solve for a, b, and c. So we got to think a little bit more carefully now about our convenient values. For example, if I let x equal -2, I would plug in a -2 right there. I would plug in a -2 right there. What that would do is cancel the c, because I get a 0 right there. It would also cancel the b, because I get a 0 right there. If b and c are canceled, that's going to allow me to solve for a. So I think -2 would be a pretty good choice. So I'm going to let x equal -2. When I do that, I'm going to have to put a -2 here and here. So -2 squared would be 4. 4 times 4 is 16. And then here, -7 times -2 is 14. 16 plus 14 is 30. And then 30 minus that 3 right there is 27. So I get 27 from the left side of the equation. If I plug in the negative 2 right there, I get negative 2 minus 1, which is negative 3. Negative 3 squared is 9. 9 times a is 9a. And remember, if I plug in the negative 2 here and the negative 2 here, b and c are just going to cancel because you get a 0. So that means that a rather is equal to 3. So one more that I noticed, if I let x equal, let's say x equals 1. If I plug in a 1 right here for that x, and I plug a 1 in here for that x, 1 take away 1 is 0, so a would cancel, and since this is 0, b would cancel, allowing me to solve for c. So I'm going to let x equal 1. So if I put in a 1 right here and right here, 1 squared is 1. 1 times 4 is 4. 4 minus 7 is negative 3, and the negative 3 minus 3 is negative 6. So I get a negative 6 from the left side of the equation. If I plug in a 1 right here and a 1 right here, I'm going to get zeros both times, so a and b are going to disappear. If I plug in a 1 right here, I get 1 plus 2, which is 3, which makes 3c, so c equals negative 2. Now, as often happens with repeated factors, we're out of convenient values. I've already used x equals 1 and x equals negative 2. Those are the only two convenient values. Problem is, I still haven't solved for b. So what you would do at this point, if you're out of convenient values, you just choose a random value, some simple number for x. I'm going to let x equal 0. But the trick now is since x equals 0 doesn't cancel any other of these other values, like it doesn't cancel the a, it doesn't cancel the b, it doesn't cancel the c, it's just a random value. But I already know that c equals negative 2 and that a equals 3. So if you're just choosing a random value for x, you need to plug in everything you know up until that point. So I know that a equals 3, and I know that c equals negative 2. So I got to plug all of this in. So if I let x equal 0, here, that's just going to result in 0 minus 3, which is negative 3. If I let x equal 0 and a equal 3, so if I do the x equals 0 here, 0 minus 1 is negative 1, but negative 1 squared is 1, and then remember a was equal to 3. 3 times 1 is 3. So from this whole expression I get a 3. Now I don't know what b equals, but remember I'm letting x equal 0, so here and here would both be 0. 0 plus 2 is 2, and then 0 minus 1 is negative 1. 2 times negative 1 is negative 2, and then negative 2 times b is negative 2b. And then here I'm letting x equal 0, so 0 plus 2 is 2, and then c equals negative 2, so 2 times negative 2 is negative 4. Now I just got to solve for b. b is the only variable left in this equation, so if I combine the 3 and the negative 4, that makes negative 1. And then if I add that to the other side, I'm going to get a negative 2 equals negative 2b, and then b is going to equal 1. So now I know all the values for my partial fractions, so I just need to rewrite them. Instead of a over x plus 2, I'm going to have, well, not a, I know that a equals 3 now, so I'm going to have 3 over x plus 2. And then I know that b equals 1, so this is going to be 1 over x minus 1. And then I know that c equals negative 2, so it's going to be negative 2 over x minus 1 squared. Okay, so question 6 is from section 5.4, solving nonlinear systems of equations.
This is not going to work with elimination, because if you notice, x squared and x, those aren't going to eliminate because they're not like terms, and then y squared and y, those aren't like terms either, so those can't eliminate. So I'm going to do the substitution method. So if I rewrite this bottom equation, I can write it as y equals x plus 2 if I just move the x over. And then I can take this expression, x plus 2, and substitute it in for that y right there. Because y equals x plus 2, and in both of these equations, y equals the same value. So this top equation now can be written as x squared, and then instead of y squared, it's x plus 2 squared. And that equals 8. Now simplify here, you're going to have x squared plus, and then if you simplify the parenthesis, x squared to the second, or x plus 2 to the second power is x squared plus 4x plus 4, and that equals 8. So this becomes 2x squared plus 4x. If you subtract the 8 to get one side equal to 0, you get minus 4. That equals 0. Now we can divide everything by 2.
And when you get to this stage, oftentimes you can easily solve this quadratic equation by either factoring or using square roots. Unfortunately, this one is a little different. It's less common, but it does happen from time to time where you have to solve at this point using the quadratic formula. So x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. So inside the square root, we're going to get 4 plus 8, which is 12. And the square root of 12, let me erase that over here. The square root of 12 is 2 times the square root of 3. And then since we have a number here, here, and here, this is the only time that we can simplify this kind of an expression, when you have numbers in all three spots that have a common factor. If you divide all of them by 2, you're going to get negative 1 plus or minus the square root of 3. And this is the value of x. That's actually two different numbers. So what we're going to have are 2 points where these two graphs intersect. Because remember, here we have a circle and we have a line right there, so the line goes through the circle twice. So we need to know the x and y values where that occurs. We know the x values now. One of them is negative 1 plus the square root of 3. The other point has an x value of negative 1 minus the square root of 3. So all we got to do is find the y values. Well, we know that y equals x plus 2. We know that from over here, y is equal to x plus 2. So when x equals negative 1 plus the square root of 3, then we could say that y equals, instead of x plus 2, it's this expression here for x, negative 1 plus the square root of 3 plus 2. So if you add the negative 1 and the 2, you get 1 plus the square root of 3. Excuse me. If we do the other value of x, when x equals negative 1 minus the square root of 3. Then y still equals x plus 2, but I'm going to substitute that expression for x. Negative 1 minus the square root of 3 plus 2. If we combine, we're going to get 1. So we're going to get 1 minus the square root of 3. So these are the two y values. This one pairs up with that x values, so I'm going to transfer that here, 1 plus the square root of 3. And then this y value matches up with that x value. So I'm going to write it here, 1 minus the square root of 3.
All right, question 7. We're going to need to graph a system of linear inequalities. This is from section 5.5. Okay, so obviously we're going to need a graph. This first one here, x plus 2y is greater than 4. If I want to find the x-intercept, I let y equal 0, so the x-intercept is 4. If I want to find the y-intercept, I let x equal 0, so the y-intercept is 2. And since it's just greater than or not greater than or equal to, it's going to be a dotted line. Let's try that again. And now we need to figure out where to shade. So if I choose a test point 0, 0, I would end up with x plus 2y would be 0 plus 0. So I'd have a statement that 0 is greater than 4. That's not true, so the test point I chose, 0, 0, isn't in the shaded region. So for this line, the shaded region is above. So I'm shading above the line. Now this next one, y is less than 1. If you have y equals a number with no x, that's just a horizontal line. So this is a horizontal line that goes through 1 on the y-axis. And I'm making it dotted because it's greater than or not greater than or equal to. And y is less than 1 means we're shading beneath it, so I need to shade beneath that line I just drew. So far, this area right here, that's the double shaded region so far, but we have one more equation. X is greater than or equal to 0. Remember, if you have x equals a number, that's a vertical line. So x equals, or x is greater than or equal to 0 is a vertical line that goes right here through 0. So there's that one there. And shading greater than 0 means we're shading to the right. So the area that would contain all three shades is this area right here. So it says label the vertices with the coordinates. The vertices, remember, is where on the shaded region the graphs intersect with each other. So right here we have an intersection here. The other parts of this shaded region, though, it's what's called unbounded, because it continues on in that direction, it continues on in this direction,
without bound. And so this shaded region is just going to keep getting bigger and bigger and bigger. So the only boundary really of this shaded region is this point right here. So we just need to figure out the coordinates of that one point. Now that one point happens to be the intersection of two lines. It's this horizontal line. I'm going to highlight it here in a different color. This horizontal line right here, this one in red. And this line right here, it's the intersection of those two lines. So we already know the y-coordinate. Because it's on this horizontal line, y equals 1. The point right there, since it's on the line y equals 1, it has to have a y-coordinate of 1. That comes from this line right here. This is telling us that y equals 1. Now it's also on this line here. We need to find x, but we know that y is equal to 1. So if you just solve that simple equation, subtract 2 from both sides, you get x equals 2. So that point there is the point 2, 1. And part B, same type of thing. Graphs are going to be a bit different. Let's try that again. That top one, x squared plus y squared is less than 9. That's a circle with a radius of 3, center at 0, 0. So do your best to draw a circle there, and since it's less than or not less than or equal to, it's a dotted circle. And then we need to figure out where to shade. If we do a test point, like this test point here, 0, 0, we would plug a 0 in for x and y, and we would get the statement 0 is less than 9, which is true. So we need to shade the part where the test point was, and that was inside the circle. So shading inside the circle. So this other equation, x squared plus y is less than 3. If we get y by itself, we can write this as y is less than negative x squared plus 3, which is a parabola upside down because of that minus sign there, and it's been moved up 3 units because of that plus sign there, that plus 3. So if we go up 3, that would be the vertex right there, a little blue point. Then we need a few other points on the parabola, and since it's less than or not less than or equal to, this one is also a dotted parabola. And then we need to figure out where to shade. So we can do the same test point, this test point here, 0, 0. If you plug a 0 in back in the original here, let me erase this. If we plug a 0 in for both x and y, we get the statement 0 is less than 3, which is true. So we need to shade, for this parabola, we need to shade where the test point was. The test point, remember, was here at 0, 0. And since it satisfied the inequality, we need to shade inside. So shading inside the parabola, you need to consider the double shaded region. So I'm going to just shade the double shaded part. That would be inside the parabola and inside the circle. So this blue looking color here, this is what constitutes the double shaded or the solution set to this inequality. Okay, now we need the vertices. It's where the parabola and the circle intersect, and I can see 3 of them. We've got one right here, one right here, and one right there. So this one at the top obviously is the vertex of the parabola. It's also the outer boundary of the circle right there on the y-axis. That one's pretty easy to tell, 0, 3. These other two, so this one and that one, we're going to have to solve the system of equations. X squared plus y squared equals 9, and x squared plus y equals 3. We need to solve that system of equations. That's coming straight from over here. You just remember, change the less than or equal to's and greater than or equal to's into equal to's. So this one we can actually solve by elimination because we have like terms there. They're both x squared. Excuse me. So x squared, subtract x squared, those cancel out. Y squared, take away y, is y squared minus y. And then 9 minus 3 is equal to 6. So now we just solve this by factoring. Let's get y equals 3 and y equals negative 2. So I'm going to write this up here. When y equals 3, I'm going to use this equation here to solve for x. X squared plus, instead of x squared plus y, it's going to be x squared plus 3 equals 3. That means x squared equals 0. Therefore, x equals 0. When, however, y equals negative 2. So I've already done y equals 3. Now I got to do y equals negative 2. When y equals negative 2, we get x squared plus negative 2 equals 3. Add 2 to both sides and you get x squared equals 5. Square root on both sides and you get x equals plus or minus the square root of 5. So over here, this one we already knew was the point 0, 3. This one now is the point plus or minus square root of 5, negative 2. So x can be positive square root of 5 and y is negative 2, and then x could be negative square root of 5 and y is still negative 2. So what that looks like, this point over here then would be the positive square root of 5 for x, and y equals -2. And this one over here would be the negative square root of 5 and y equals -2. Okay, number 8. This is linear programming. We have the objective function, and we want to try to find the maximum value of z. That means we have to plug points in for x and y, or plug values in for x and y. X and y are points on a graph, and we get those points from the feasible region from that inequality set right there. So we need to graph those. Okay, let's start with this one. X is greater than or equal to 0. X equals a number is a vertical line, so if x equals 0 or greater than or equal to 0, that's a vertical line that goes right through the y-axis right here. So there's our first inequality. And we're going to be shading greater than 0, which is this direction. So anything in that direction is going to be shaded. So I'm going to erase that shading for right now and just remember that I'm shading to the right. Otherwise, this is going to get a little messy. Now, this middle one here, y is less than or equal to negative x plus 4. That's just the slope-intercept form of a line. The y-intercept is 4, and the slope is -1, so down 1 over 1. And since it's less than or equal to, it's going to be a solid line. And then we need to figure out where to shade. So I'm going to choose a test point. This test point right here, 0, 0. That means I plug in a 0 for y and a 0 for x. 0 plus 4 on the right side is 4, so you end up with the statement 0 is less than or equal to 4. 0 is less than or equal to 4. That's a true statement. So on this line, we would be shading towards where the test point was, so that would be this direction. But remember, we also have to shade to the right of the line x equals 0. So far, the double shaded region would be to the right of the y-axis and underneath this line. Okay, so I'm going to go ahead and erase the shade so I can see the other line. This last line, y is greater than or equal to x. That's a line where y and x have the same value, because what it says y equals x. So like 1, 1, y and x have the same value. And then 2, 2, y and x have the same value. And 3, 3, that's the line where y and x have the exact same value. Or another way you could think about it in slope-intercept form, it's y equals 1x plus 0. So the y-intercept is 0 and the slope is 1. It's another way to think about it. It's greater than or equal to, so it's going to be a solid line. Now we need to figure out where to shade. Now this is the one instant where we can't use the test point 0, 0, because this line goes right through 0, 0. You can't use a test point if it's right on the line. So you can use a point that's not on the line, like that point there. That's the point 0, 1. We can use that as a test point. That means x is 0 and y is 1. So we have the statement 1 is greater than or equal to 0. That's true. So we would need to shade towards that test point. So that would be this direction above that line. So now we got to keep track of where we're shading. Remember, we were shading to the right there. We were shading Let's get that line back. There it is. And we were shading underneath that one. And we were shading above this one. So this little shape that would contain all three of the shaded portions would be this little triangle right in here. This is what's called a bounded. We have three vertices now. We've got this one here, and that one there. This one, it's pretty easy to tell that it's 0, 4. This one is the origin 0, 0. This one is the intersection of two lines. It's the intersection of the line y equals x and the line y equals negative x plus 4. So we need to solve this system of equations. If y is equal to x, but y is also equal to negative x plus 4, if both of these expressions here are equal to y, that means those two expressions are equal to each other. X is equal to negative x plus 4. So x is equal to negative x plus 4. So if you add x to both sides, you get 2x equals 4. So x equals 2. And then according to this, y is equal to x. So that also means that y is equal to 2. So that's the point 2, 2.
All right, once we have the boundary points of the feasible region, the last task is to actually answer the question, which is to maximize our objective function, but we needed to know our x and y values here. So we need to find the value of z for each one of these boundary points there. So the value of z with the point 0, 0, if I plug in a 0 for both the x and y there, I'm just going to get 0. The value of z for the point 2, 2, well, that's 4 times 2, which is 8, and then 3 times 2, which is 6, and that equals 14. The value of z for the point 0, 4, that's 4 times 0, which is 0, and then 3 times 4, which is 12, so that equals 12. It looks like that's our maximum value there. So the point 2, 2 maximizes your...
Okay, question 9 is from section 6.1, where we're practicing row operations, among other things. So looking at this first row operation here, we're going to do row 3, and we're going to subtract 2 times row 2. And that's going to become a new row 3. So looks like both of these row operations are just affecting row 3 and row 4. So I can actually just write row 1. All this line right here is, sometimes they put these in augmented matrices, and all that denotes is, that's where the equal sign would go. So these, let me erase this. These numbers would be coefficients. These numbers on this side would be coefficients, and then these would be after the equal sign. And that's what this line here is telling you. That's where the equal sign goes. That's all it is. All right, let's do this first row operation. Row 3 minus 2 times row 2. So this is row 3 right here. So starting with that, row 3, that would be 0, minus 2 times row 2 here, still 0. That becomes a new row 3. So 0. Now move over here. We're going to use these two numbers. So row 3, which is 2, minus 2 times row 2, which makes that 2. 2 minus 2 is 0. Now using that part of row 2 and row 3, so row 3 minus 2 times row 2. So that would be negative 3 minus 4, it's negative 7. Now moving over to here, 0 minus 2 times negative 3. So that's 0 minus negative 6, that's a positive 6. Then over here, negative 1 minus 2 times negative 2, so that's minus negative 4. Negative 1 minus negative 4, it's negative 1 plus 4, which is 3. Now let's do this row operation. This is going to use row 4 and row 2. And that's going to replace row 4. So I need row 4 and row 2. So row 4 plus 3 times row 2 is going to be 0 plus 0. And then row 4 plus 3 times row 2, so negative 3 plus 3 times 1. That's negative 3 plus 3, which is 0. Now here, row 4 plus 3 times row 2, so 3 times 2 is 6, 2 plus 6 is 8. Now we go here and here, negative 1 plus 3 times negative 3, that's negative 9. Negative 1 plus negative 9 is negative 10. And then here and here, so we have negative 3 plus 3 times negative 2. 3 times negative 2 is negative 6, so we've got negative 3 plus negative 6 is negative 9. Okay, these are never fun, these Gaussian elimination problems. It starts with the augmented matrix. So we've already got a 1 right here, which is great. So remember, now we need to get a 0. We need to get a 0 here. We need to get a 0 here. So first row operation I'm going to do is negative 2 times row 1. I'm going to add that to row 2. That's going to become row 2. So negative 2 times that is negative 2. Negative 2 plus 2 is 0. Negative 2 times right there is negative 4. Negative 4 plus negative 1 is negative 5. Negative 2 times negative 1 is 2. 2 plus 3 is 5. And then negative 2 times 6 is negative 12. Negative 12 plus negative 13 is negative 25. I also want to get a 0 right here, and that's affecting row 3, so I'm going to do a new row operation. It's going to be negative 3 now times row 1. I'm going to add that to row 3. That becomes row 3. So negative 3 times right there times 1, that's negative 3. Negative 3 plus 3 is 0. Negative 3 times row 1, that makes negative 6. Negative 6 plus negative 2 is negative 8. Now negative 3 times right there is, so negative 3 times negative 1 is 3. 3 plus 3 is 6. And then negative 3 times 6 is negative 18. And then you get negative 18 plus 16. That's negative 34. then row 1 stays the same. So now I want to get a 1 right here where that -5 is. That should be a 1. So what I'm going to do is multiply -1/5 times row 2. Essentially, I'm just going to divide row 2 by -5. That's all that's doing. That's going to become a new row 2. So now that I've got the 1 right here, I need to get a 0 right there. So the next row operation, I can do, excuse me, 8. If we multiply row 2, so 8 times row 2, if I now add that to row 3, let me write this sideways. 8 times row 2. That's not working much better. So 8 times row 2 plus row 3. And that's going to become row 3. There we go. So multiplying, well, let's start at the beginning of the row just to make sure we don't undo something we already did. If we multiply there by 8 and then add it to there, we still get 0. Now right here, 8 times 1 is 8, 8 plus -8 is 0. Now right here, -1 times 8 is -8, -8 plus 6 is -2, and then right there, 8 times 5 is 40, 40 minus 34 is 6. So now we're ready to start backward substituting. This bottom row right there represents the equation -2z is equal to 6. Therefore z equals -3. And then this middle row represents the equation y minus z equals 5. But we know that z is -3, so we got y minus -3 equals 5. Minus the negative is +3, so you got to subtract it on both sides, and you get y equals 2. Now this top row represents the equation x plus 2y minus z equals 6. So that means x plus 2, and then y was equal to 2. So that's 2 times 2 minus -3 equals 6. So we have 4 plus 3, that's 7. So you got to subtract 7 on both sides and get x equals -1. So the solution is -1, comma 2, comma -3. So I want us to do a times b and then b times a. Remember, when you multiply matrices, it's not commutative, meaning a times b isn't the same as b times a. So a is a 3 by 3, and b is a 2 by 3. So if we're going to do this direction, if we want to do that direction there, a times b, it's actually not going to work. Remember, those inside dimensions have to match. They don't. So a times b is not possible. Now b times a, B is a 2 by 3 matrix and A is a 3 by 3 matrix, those dimensions do match. So B times A is possible. So B and then multiply that by A these numbers here tell us that the result of this multiplication is going to be a 2 by 3 matrix. So that means 2 rows and 3 columns. Alright, this entry right here is in row 1, column 1, so I need row 1 and column 1. So I'm going to start with the 0 and the 1. 0 times 1 is 0. Now move across the row to this number and down the column to that number. 2 times 0 is 0, so I'm going to add 0. Now move across the row to this number, down the column to that number. 1 times 5 is 5, positive 5, so I'm going to add 5. Now if I want this entry right here, that's row 1 but column 2, so I'm going to keep it on row 1, but now I'm going to move to column 2 here. So starting in row 1, I need this number times that number. Start of the row, top of the column, so that's 0 times 1, which is 0. Now move across the row to that number, down the column to that number. 2 times 3 is plus 6. Now move across the row, down the column to those two numbers. 1 times 0 is 0. Now, if I want this entry there, that's in row 1, now to column 3. So start of the column, or start of the row there, top of the column, 0 times negative 1 is 0. And then move across the row, down the column, 2 times 1 is 2. And then move across the row, down the column, 1 times negative 2 is negative 2. Excuse me. So now I need this entry, which is row 2 now, and column 1. So start at the beginning of the row, top of column, 3 times 1 is 3. Move across the row, down the column, negative 2 times 0 is 0. Move across the row, down the column there, 4 times 5 is 20. Now move over, if I want this entry, that's row 2, column 2, so row 2, column 2 would be right there. Start of the row, top of the column, 3 times 1 is 3. Move over, move across the row, down the column, negative 2 times 3 is negative 6. Now move across the row, down the column, 4 times 0 is 0. Now I need this entry, which is in row 2, column 3. So start of the row, top of the column, 3 times negative 1
is -3. Move across the row, down the column, -2 times 1 is -2. Move across the row, down the column, 4 times -2 is -8. So adding this all up, row 1, column 1, 0 plus 0 plus 5, that's 5. Then we got 0 plus 6 plus 0, that's 6. 0 plus 2 minus 2 is 0. Second row, we're going to have 3 plus 0 plus 20, that's 23. 3 minus 6 plus 0 is -3, and -3 minus 2 is -5. -5 minus 8 is -13. All right. Question number 12 is from section 6.3, finding the inverse. We have a 2 by 2 and a 3 by 3. The 2 by 2 has a very simple formula. It's 1 over AD minus BC, and then inside the matrix you switch the spot of A and D and change the sign of B and C. Remember where this is A, B, C, and D. So the inverse is going to be 1 over AD there, which is -10, minus BC, which is there, that's 12. And then inside, these two numbers switch spots. And then these two numbers change sign. So the inverse is -1 over 22 like that. Unfortunately, a 3 by 3 matrix is a lot more intense. So it starts with a super augmented matrix. And then we have a little bar there. Then the right side is the identity matrix for a 3 by 3, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Now the point is to turn this left side into the identity matrix. We need to perform row operations so that that left side looks like that right side, 1, 0, 0, 0, 1, 0, 0, 0, 1. By doing those row operations, this side here is going to change into different numbers, and whatever it changes into at the end is your inverse. So we need to get 1 right there and then zeros underneath it. So there's a couple of things we can do. Honestly, sometimes the quickest way, if you just want to get something to be a 1, is to divide by whatever the number is that is there now. So if there's a 2 right there, if I divide everything in that row by 2 or multiply it by 1/2, that's going to change that into a 1. So we could just do 1/2 times row 1, and that's going to equal the new row 1. And remember the point there is just to get a 1 right here, because 1/2 times 2 is 1, and then 1/2 times 4 is 2. 1/2 times 1 is 1/2. Unfortunately, often with these inverses, there's just no way you can get around having to deal with fractions at times. 1/2 times 1 is 1/2. 1/2 times 0 is 0, and 1/2 times 0 is 0. Okay.
So now we need to get a 0 right here. And we need to get a 0 right here. So what we could do is negative 1 times row 1, add that to row 2, and that becomes a new row 2. So negative 1 times row 1 right there, and then add it to row 2, that becomes negative 1 plus 1, which is 0. Now negative 1 times there would be negative 2. Negative 2 plus 1 is negative 1. Negative 1 times that is negative 1/2. Negative 1/2 minus 1 is negative 3/2. And then negative 1 times there is negative 1/2. Negative 1/2 plus 0 is negative 1/2. And then negative 1 times there is 0. 0 plus 1 is 1. And then there, 0 plus 0 is going to be 0. Now we could also try to get a 0 right there by doing a very similar operation. We could do negative 1 times row 1, add that to row 3, and that can become row 3. So negative 1 times row 1, that would be negative 1 times 1, and then add that to row 3 there. Negative 1 plus 1 is 0. Now go here, negative 1 times 2 is negative 2. Negative 2 plus that 1 right there is negative 1. Then negative 1 times 1/2 is negative 1/2, and then add it to the 0, and it stays negative 1/2. Negative 1 times that 1/2 is negative 1/2. Added to that 0 is negative 1/2. Here we're going to get negative 1/2 plus 0. 0 plus 0 is 0. Here we get negative 1/2 times 0, which is 0. 0 plus 1 right there is 1. So now right here there should be a 1, and there's a negative 1, so what I'm going to do is just multiply row 2 by negative 1 to get that to be a positive 1. So negative 1 times row 2 equals row 2. So all that does, like I said, is change the sign of every entry in row 2. So 0, positive 1, positive 3/2, positive 1/2, negative 1, and 0. Okay, now we should get a 0 right here. So we could just add row 2 and row 3 and make that a new row 3. So that's what I'm going to do there. Row 2 plus row 3 equals row 3. So here we get 0 plus 0, that's 0. Here we get 1 plus negative 1, that's 0. Here we get, if we add those two, we get 3/2 minus 1/2, that's 2/2, or just 1. Here we're going to get 1/2 minus 1/2, which is 0. Here we're going to get negative 1 plus 0, which is negative 1. Here we're going to get 0 plus 1, which is 1. We also need to get that to be a 0. So if I multiply row 2, if I multiply row 2 by negative 2 and then add those, and call that row 1, that would do it. So I'm going to do -2 times row 2, add that to row 1, that becomes a new row 1. So -2 times 0 was 0, 0 plus 1 is still 1. -2 times that 1 is -2, -2 plus that 2 right there is 0. Sorry. -2 times 3/2 is -3. And then -3 plus 1/2. So we have -3 plus 1/2. That's -5/2. And then here we've got -2 times row 2. So -2 times 1/2 is -1. -1 plus 1/2 is -1/2. And here we have -2 times -1, that's 2. 2 plus 0 is 2. And then here we're going to have 0 plus that 0 is 0. So now that we have a 1 right here, we need to get a 0 right there and a 0 right there. So I'm going to use this 1 and multiply it by the opposite here, which would be -3/2. So this is going to be -3/2 times row 3, add that to row 2, and that becomes a new row 2. So -3/2 there is 0, 0 plus 0 is 0. -3/2 there is 0, 0 plus 1 is 1. -3/2 there is -3/2. -3/2 plus 3/2 is 0. -3/2 there times 0 is 0, 0 plus 1/2 is 1/2. -3/2 times -1 is 3/2. 3/2 minus 1 is 1/2. Oops. 1/2. And then -3/2 times 1 right there is -3/2. -3/2 plus 0 is -3/2. Now I also want a 0 right there. So I'm going to use this 1 again and multiply it by the opposite, which is +5/2. So 5/2 times row 3. Now I'm going to add that to row 1. That's going to become a new row 1. So starting there, 5/2 times 0 is 0. 0 plus 1 is 1. Right there, 5/2 times 0 is 0. 0 plus that 0 is 0. Now here, 5/2 times 1 is 5/2. 5/2 plus that -5/2 there is 0. And then here, 5/2 times 0 is 0. 0 plus -1/2 is -1/2. And then here, 5/2 times -1 is -5/2. And then -5/2 plus 2. So we got -5/2 plus 2. That's going to be -1/2. And then here, 5/2 times 1 is 5/2. 5/2 plus that 0 there is 5/2. So this now is the inverse. Because we have the identity matrix over here on the right side, sorry, on the left side. So the inverse of A is equal to this guy. All right, 13. Apply matrix algebra to solve the system of linear equations. So we need to set up a matrix equation where we have a matrix A and then a coefficient or a variable matrix, and that's going to equal the matrix B, which is just this matrix right here. So what this looks like is a coefficient matrix A, 4, 3, -3, -2. So that's matrix A here, and then we have the variable matrix X, Y. This is like the matrix X. And then we have that there. So symbolically we have the equation AX equals B. So let me write this over here. If we've got matrix A times matrix X, and that's equal to B, if I want to get X by itself, remember you can't divide by matrices, there's no such thing. But if I multiplied by the inverse of A, that would cancel it out, and then I could do the inverse of A over here. So then the solution is X equals the inverse of A times B. So this is what we're going after, the inverse of A times B. So first over here I need to find the inverse of A. And remember, the inverse of a 2 by 2 matrix is 1 over AD, which is -8, minus BC here, which is -9. And then inside the matrix, A and D here switch spots. And then B and C there change signs, so that becomes a +3, that makes a -3. So it's 1 over -8 minus -8 plus 9, which is 1. So there's the inverse. Now I've got to multiply that by B matrix, which is 10 and 30. So whatever the result of that product, the inverse of A times B, that's going to be my solution. So here we've got a 2 by 2, and this is a 2 by 1. So the inside dimensions match. The outside dimensions here tell us that we're going to get a 2 by 1 matrix. And then this 1 over 1 is going to be on the outside of that. So this entry right here is in row 1, which is row 1, and then column 1 right there. So start at the beginning of the row, top of the column, that's -2 times 10, that's -20. Then move across the row, down the column, 3 times 30 is 90. Okay, in this entry here, that's row 2 now and column 1. So start at the beginning of the row, top of the column there, we got -10 times, or -3 times 10 is -30. And then move over and move down, 4 times 30 is 120. So we've got -20 plus 90, that's 70, and then you've got to multiply it by what's out in front there. 70 times 1 is 70, and then here -30 plus 120, that's 90, and then you multiply that by what's out there. 90 times 1 over 1 is 90, so X equals 70 y equals 90, so the solution is 70, 90. All right, 6.4, determinants, and then later on Kramer's rule. The determinant of a 2 by 2 is pretty easy. It's AD right here, which is -4. Then you subtract this direction. That product is +6. So we get -10. A little different for a 3 by 3. The method I showed you on the review is the same method our book uses. It's a method that works okay. There's another method that during the practice exam some of the students preferred. So I'll show you that method. That method is you take this first column and write it here. And then you take the middle column there and write it here. And then you find a bunch of products and add and subtract them. You need to find this product, and that product. So this product here is 2 times -7 times 0, which is 0. And then you add that to this product, which is 1 times 0 times 4, which is 0. And then you add it to this product, which is -5 times 3 times -6. That's 90. Then you find products going in this direction, and those products you subtract. So this direction here, we're going to have 4 times 7. Let's see, 4 times -7 times -5. That's 20 times 7, that's 104, that's positive 140, but we're going to subtract it because it's going that direction. So -140, and then we've got this product there, -6 times 0 is 0, so subtract 0. And then this product there, 0 times 3 times 1 is 0, so -0. So we have 90 minus 140, which is -50. So that's one way you can do it. I'm fine if you use that method. Let me erase this, and I would, at least for this matrix, I would actually use the way I showed you in the review. The reason is you've got a column here that's got 2 zeros in it, so that other method is going to go pretty quick. So with that other method that I used on the review is you choose a row or a column. I'm going to choose that column right there because it has these 2 zeros. So you choose the top number there, -5, and then you multiply it by the determinant of a matrix that would occur if you cross out that row and column. So you're going to have 3, -7, 4, -6. And then you move down the column that you've chosen. So now we've got that. So 0 multiplied by the determinant of, when you cross out that row and column, you're going to have 2, 1, and then 4, -6. Then you move down the column that you've chosen, there's another 0 there, so 0, and then you cross out that row and column. That leaves the smaller matrix 2, 1, 3, -7. And then to figure out whether you add or subtract all of those, that last column follows the pattern plus, minus, plus, so you're going to subtract that one, add that one. But the nice thing is 0 times that is 0, 0 times that is 0, so those just disappear. So really all I got to figure out is that's -5 times this determinant, -18, minus that one is -28. Well, minus a negative is plus. -18 plus 28 is 10. -5 times 10 is negative 50. So you get the same answer. I don't care which method you use to find the determinant, you just gotta find the determinant correctly. Okay, last question 15, Kramer's rule. This is from section 6.4. Kramer's rule uses a bunch of determinants. If you have two equations and two variables, you need three determinants. You need d, you need d sub x, and you need d sub y. Now the first determinant d, that's just the coefficients of the variables. So remember the determinant of a 2 by 2 is that product there, which is 12, minus that product there, which is negative 10. So that equals 22. Now d sub x, you got to pay attention to the subscript, because that tells you that in the x column, which is here, you're going to put these values, negative 1 and negative 31. Those go in the x column. The other column is the same as it was in the original matrix, negative 2, 4, and then you find this determinant. So you need this cross product, which is negative 4, subtract that one there, which is 62. So that's negative 66. Now for the determinant with a subscript of y, now since there's a subscript of y, we're going to put that negative 1 and the negative 31 in the y column. And then the x column is the same as it was in the original matrix, 3, 5. We find this determinant, negative 31 times 3 is negative 93, and then subtract that cross product there, which is negative 5. So negative 93 plus 5 is negative 88. And now here's Kramer's rule. It says x is equal to the value of d sub x divided by d. That's negative 66. So d sub x was here, and the d value was there. So it's negative 66 divided by 22, which is negative 3. And then y is equal to d sub y divided by d. So d sub y was here, and d again was 22. Negative 88 divided by 22 is negative 4. So the solution is negative 3, comma, negative 4. Okay. Kramer's rule is pretty much the same for 3 variables and 3 equations. You just need one more determinant. We still need the d. We need d sub x. We're going to need d sub y. And because we have another variable, we're going to need d sub z. So the d determinant is just the coefficients. And you can use either method. You can use any of the two methods I've shown you for determinants. I'm going to go ahead and use this one where you copy these columns. So this is just that column right there. Then you take that middle column, so now the determinant, we need this product, which is negative 1. This product is also, so you add negative 1, and then this product is 1. Now we find the products going the other way. That product there is 1, but since it's going the other way, we subtract it, so minus 1. Then we have this product, 1 times negative 1 times negative 1, that's 1. But since we're going that direction, we subtract it. Anything in that direction is subtracted. And there, we have 1 times 1 times 1, which is 1, but then we subtract it. So those ones are going to cancel. We have -1, -1, -1, -1. That's -4. Okay, so d sub x now the x column is going to take on those values there, -4, 0, and 2. And then everything else is the same as it was to start with. So we need to find that determinant. We use the same method, so repeat the first column and repeat the second column. So that product there is 2, that product there is 4, and that product there is 0. Now we start subtracting. Actually, I did that in the wrong direction. It's this product there is -4. We add that to this product there, which is -2, and we add it to that product there, which is 0. Now we start subtracting this direction. That product is 2, and then we subtract that product, which is 4, and then we subtract that product, which is 0. So it looks like we're going to get -4 minus 2 minus 2 minus 4. That's -12. Okay, d sub y. Now the y column, the middle column, takes these values there. And then the x and y, or the x and z columns were the same as they were to start with. And I'm going to use that other method, -1, 1, 1. So repeat the first column and repeat the second column. That product is 0. That product, we're going to add it, and that product is 4. And we're going to add this product, which is 2. Now we start subtracting that direction. That product is 0. That product subtract is 2, and then that product is -4, but we subtract -4. So the 2 and the -2 would cancel. We've got 4 plus 4, so that would be 8. And lastly here, the subscript of z means that the z column now takes that value, -4, 0, and 2. And then the x column is the same as it was originally. And the y column is the same as it was originally. All right, that product is -2. We add that to this product, which is 0, and we add it to that product, which is -4. And then we start subtracting that direction. And subtract that one. And subtract that one. Okay, that becomes a plus, so the 4's cancel. -2 and a -2 right there makes -4. So x is equal to d sub x over d. Y is equal to d sub y over d. And z is equal to d sub z over d. So the d determinant was -4, the d sub x was -12, so this is -12 over -4, so that equals 3. The d sub y determinant was 8, and the D determinant was a -4. So that equals -2. And over here, the D sub Z was -4. The D determinant was -4. So we get 1.